Good morning to all. Today's lecture we see one more theorem is there. Theorem. In the last lecture we seen that what is the invariant direct sum. Okay. So today we will discuss about one more theorem. Okay. So look at the theorem. What is the statement? Let T be a linear operator on finite dimensional vector space V. Okay. Let T be a linear operator on a finite dimensional vector space V over F, and let V is equal to direct sum of W1 plus W2 plus up to Wk. Okay. Let V be a direct sum of W1 plus W2 up to Wk. Also, this is the statement of the theorem. Also, there exists k linear operators E1, E2 up to Ek. Okay. There exists k linear operator E1, E2 up to Ek such that Ek on V on vector space V. There exist a k linear operators E1, E2, Ek on V such that first condition. What is the first condition? Each EI is projection on V. Each EI is projection on V. Okay, that is square EI square equal to EI for on I. Each EI is projection on V, that is EI square is equal to I. Second condition. What is second condition? EI into EJ. EI into EJ is equal to 0. EI into EJ is equal to 0 for I not equal to J. Third condition. Okay, third condition. I is equal to E1 plus E2 plus up to Ek. Okay, this is the third condition. Fourth condition. Range of EI. Range of EI is Wi. That is, for any vector alpha, EI of alpha belongs to Wi. That is, range of EI is Wi. Then the necessary and sufficient condition. Then this is the statement in this all these given things. Then necessary and sufficient condition for the necessary and sufficient condition is that each subspace Wi, okay, each subspace Wi is invariant under T. Is invariant under T is that commits T commits with each of the projection EI, that is T into EI is equal to EI into T. Okay, T into EI is equal to EI into T. What says the theorem? Look at the theorem once again. Let T be a linear operator on a finite dimensional vector space V, and let V is equal to direct sum of W1, W2 up to Wk. Okay. Also, there exist k linear operators such that E1, E2, Ek. These are the k linear operators on V, such that these all the EIs satisfies this condition. Okay. What are the condition? Each EI is the projection on V. That is EI square is equal to EI. Okay. EI into EJ is equal to 0 for I not equal to J, and I is equal to E1 plus E2 plus up to Ek, and range of EI is Wi. Then this is all the given things are there. Then the necessary and sufficient condition that each subspace Wi is invariant under T. What is the necessary and sufficient condition for each subspace Wi? Wi is invariant under T is that T commutes with each of the projection EI. Okay, that is EI into T into EI is equal to EI into T. Okay, first we prove the sufficient condition assuming each EI is commuting with each T, and assuming this condition we have to prove Wi is invariant under T. Okay. Okay. The necessary condition proof. Okay. Proof. Sufficient condition. Okay, what is the sufficient condition? Look, suppose T commutes with each of the projection EI for I equal to 1, 2 up to k. Okay, that is T into EI is equal to EI into T. To prove that, what we have to prove? Wi is invariant under T. Okay, Wi is invariant under T. That is to prove if alpha belongs to Wi, okay, T of Wi contained in Wi. Okay, we have to prove this. T of Wi is contained in Wi, assuming T into EI is equal to EI into T. Okay, for this, first we assume let alpha belongs to Wi. Okay, alpha belongs to Wi. Then be any vector. Alpha belongs to Wi be any vector. any vector in Wi. Okay. Okay. So then by definition of AI, in the previous theorem we see the definition of AI. What is it? AI by definition of AI. By definition of AI, EI of alpha is equal to alpha. Okay. How it is? If here alpha belongs to Wi, hence each EI operates like identity operator. Why? Because alpha belongs to Wi. Okay. Hence EI of alpha is alpha. EI is like identity operator if alpha belongs to Wi. EI operates like identity operator on Wi. Okay, this is the reason. So EI of alpha is equal to alpha. Now it implies, what implies? EI of alpha belongs to Wi. Okay, EI of alpha belongs to Wi. Why? Because range of EI is Wi by second condition. Okay, this EI of alpha goes to Wi because range of EI is Wi. Hence, next, consider you know that EI of alpha belongs to Wi. Consider what we have to consider. T of alpha, which is equal to T of alpha means EI of alpha. Alpha is equal to EI of alpha, na? So we can write alpha as EI of alpha. Okay. Give it as equation number 1. Okay. The EI of alpha, T of alpha is equal to T of EI of alpha. Okay. Give this as equation number 2. EI of alpha is equal to alpha is equal to, give it as equation 2, and EI of alpha, this is equation number 3. Okay. So considering T of alpha is equal to T, alpha means EI of alpha. Okay. Now, but T it competes with each EI. So EI into T of alpha. Since T into EI is equal to EI into T by assumption, na? Okay. So we can write T into EI is equal to EI into T. Okay. Now, which is equal to EI into T into T of alpha. So T of alpha is equal to EI into T of alpha. Okay. The next step is that T of alpha is equal to EI into T of alpha. Give it as equation number 4. Okay. Give it as equation number 4. Since the range of EI is Wi, since range of EI is Wi, in the given condition range of EI is Wi, this EI of T of alpha, EI of T of alpha belongs to Wi. Okay. Range of EI of alpha is Wi. It implies EI of T of alpha belongs to Wi. That is, but ei of t of alpha is that what? T of alpha belongs to Wi. Okay, t of alpha belongs to Wi because the range of ei is Wi. Hence, this terms goes in Wi, which is equal to t of alpha. Hence, t of alpha belongs to Wi. Okay, t of alpha belongs to Wi. Now, we show that what we have to show, if alpha, we are taking alpha belongs to Wi, implies t of alpha belongs to Wi. Hence, for every alpha, na, for all alpha belongs to Wi, na. Hence, Wi is invariant under T. Okay, this is the necessary sufficient condition of this theorem. Okay, so Wi is invariant under T. Next, we have to show that assuming the Wi is invariant under T, we have to show each ei is commute with T. Okay, understood? If anyone who have doubt, ask me in message, ask me in WhatsApp. Okay. Now, necessary condition. Assume Wi is invariant under T. Wi is invariant under T, and to prove that T commutes with each ei, that is ei into T is equal to T into ei for I is equal to 1 to up to k, where I is equal to 1 to up to k. So assuming Wi is invariant under T, we have to prove that T commutes with each ei, that is ei into T is equal to T into ei. Okay. Now, Wi is invariant under T, na? So, what we have? T of Wi is contained in Wi. Okay, this is the definition of invariant. Wi is invariant under T. Okay, so we have I is equal to E1 plus E2 plus up to ek, na? So alpha, let for this, let alpha belongs to V. Okay, alpha belongs to V. Alpha belongs to V, be any vector, and we have P is equal to E1 plus E2 plus up to Ek. Okay. Okay, operate this t on alpha. Hence t of alpha is equal to, okay, t of alpha is equal to e1 plus e2 plus up to ek of alpha. Okay, understood? T of alpha is equal to e1 plus e2 plus up to ek of alpha. Sorry, I is equal to e1 plus e2 plus up to ek. So I of alpha is equal to alpha, which is equal to e1 of alpha plus e2 of alpha plus up to ek of alpha. Okay, I of alpha is equal to alpha and applying this alpha on each en. Okay, so e1 plus alpha plus e2 alpha plus up to ek of alpha. Hence it implies alpha is equal to summation I is equal to 1 to k ei of alpha. Okay, so this term we can write as a summation form. Okay, so alpha is equal to summation I is equal to 1 to k ei of alpha. Operates t on both sides. Operate t on both sides. Okay, operates t on both sides. Hence we get t of alpha is equal to t of summation of I is equal to 1 to k ei of alpha. Okay, so hence we get t of alpha. T of alpha is equal to summation I is equal to 1 to k. Since t is linear, hence we can write t inside the summation. Okay, t of ei of alpha. Okay, now give it as equation number 5. Okay, now ei of alpha. Now ei of alpha belongs to wi, since wi is the range of ei. Okay, ei of alpha belongs to wi, since wi is range of ei. It implies ei of alpha belongs to wi, and wi, assuming wi is invariant under t. Okay, wi is invariant under t. Hence t of ei of alpha also belongs to wi. Okay, t of ei of alpha belongs to wi. Okay, for I is equal to 1 to up to k. Okay, got it? Okay, we know that since wi is range of ei, then ei of alpha belongs to wi, but wi is invariant under t. So hence any t of alpha belongs to the wi, for any alpha belongs to wi. Okay, so this is the vector in wi. Operating t on this vector, we get t of ei of alpha belongs to wi, for I is equal to 1 to up to k. Okay, now hence we get this vector comes from wi, na? So hence ti ei of alpha, which is equal to, okay, which is equal to ei of beta. So there exists a vector beta from wi. There exists a beta belongs to v. Okay, sorry, any where there exists a beta belongs to V such that EI of beta belongs to Wi, okay, which is equal to T of EI of alpha. This vector comes from Wi. So any vector of this subspace in the form of EI of beta, okay, since EI is the range of Wi. For some beta belongs to V, okay. Why we can write like this? Because EI is the range of Wi. So there exists a beta belongs to V such that T of EI of alpha belongs to EI of beta. Okay, got it? Now, using, give it as equation number 6. Using 6 in 5, we get, okay, what we get? T of alpha is equal to summation I is equal to 1 to k EI of beta, okay, EI of beta, okay. Now operates EJ on both sides. Operates EJ. EJ is the any projection on V, okay, EJ on both sides. So it implies EJ into T of alpha, which is equal to EJ into summation I is equal to 1 to k EI of beta, okay. Okay. So EJ of T of alpha is equal to EJ of I is equal to 1 to k EI of beta. Hence, EJ of T of alpha is equal to EJ of summation I is equal to 1 to k EI of beta. Hence, run this I from 1 to k. What we have? EJ into E1 of beta plus up to EJ into EJ of beta plus 2 plus EJ into EK of beta. Okay, if I is not equal to J, then what we have? The value of these terms is 0 plus up to this is equal to EJ square, EJ into EJ square of beta plus up to k. Okay, this is the EJ of T of alpha. EJ of T of alpha. Okay, EJ of T of alpha, which is equal to EJ square means EJ of beta. Why? Because EJ is the projection on V. Hence, EJ square is equal to EJ. But from equation number 6, okay, we have from equation number 6, EJ of beta is equal to, okay, EJ of beta is equal to, from equation number 6 we have EJ of beta, here EI of beta is there, EI of beta is equal to T into AI of alpha. From replace I by J, we get EJ of beta is equal to T of EJ of alpha. Okay, so left side is EJ of T of alpha is equal to, from equation 6, T into EJ of beta. Okay, hence EJ into T of alpha is equal to, this is alpha. t into ej of alpha. Hence ej into t is equal to t into ej. Hence it implies each ei for j is equal to 1 2 2. Okay, hence each ei is commute with k. This is the proof of this theorem. Okay, this is the necessary part of this theorem. Okay, if anyone who have doubt, please ask me on WhatsApp. Okay, this is the proof of this theorem. So the next point is that the primary decomposition theorem and the definition of invariant direct sum decomposition. Okay, the definition of next point is that invariant direct sum decomposition. Okay, and one more theorem is there, primary decomposition theorem. Only statement is there, so there is no need to prove that theorem because we have a syllabus. In syllabus we have only statement. The proof is not required. Okay, before that we see the definition of invariant direct sum decomposition. Okay, invariant direct sum decomposition definition. Invariant direct sum decomposition. Okay, and after that we see the primary decomposition theorem. Okay, what is the definition? Look, let t be a